The immense scale of modern wind farms reflects the raw power of the atmospheric environment they inhabit. The atmosphere holds massive quantities of kinetic energy, moving in chaotic and unpredictable currents. Wind turbines are stationary aerospace machines engineered to intercept and extract that energy with high efficiency. Energy extraction is governed by a fundamental fluid dynamics constraint. For a turbine to capture kinetic energy, it must physically slow the air down. If a turbine were hypothetically 100% efficient, it would extract every joule of energy, causing the air velocity behind the rotor to drop to exactly zero. Such efficiency is physically impossible. If the air coming out the back stops moving, it creates a blockage that prevents any fresh wind from entering the turbine in the first place. In 1919, German physicist Albert Betz derived a theoretical limit for this extraction by modeling a turbine as an idealized actuator disk inside a fluid flow field. This visualization maps the parameters of the actuator disk model. Upstream wind velocity, labeled V1, enters the system, while the air exiting as downstream velocity, V2, moves significantly slower. Because airflow must be continuous, the principle of mass conservation dictates that as the wind slows upon exiting, the stream tube must physically expand to a wider geographic area. According to the conservation of momentum, the power extracted by the turbine is exactly equal to the loss of kinetic energy in that expanding wind stream. Betz discovered that the mathematical peak of this relationship occurs when the downstream velocity is exactly 1/3 of the upstream velocity. At this ratio, the disk captures 16/27 of the available energy. This is the Betz limit. No turbine, regardless of its mechanical design, can capture more than 59.3% of the wind's kinetic energy. Modern engineering has optimized aerodynamic profiles to the point where utility turbines can reach 80% of this theoretical limit. Wind turbine design is a masterclass in balancing fluid dynamics against this unyielding physical ceiling. Transitioning from the macro-scale fluid dynamics of the Betz limit requires looking at the micro-aerodynamics of a single rotor blade. This diagram illustrates the airfoil profile of a blade cross-section. Air traveling faster over the curved upper surface creates a low-pressure pocket. This generates a lift vector pulling perpendicular to the wind, while a drag vector pushes parallel to the flow. Efficient operation relies on the lift force substantially overpowering the drag force. This unequal pressure distribution converts aerodynamic lift across the rotor into massive mechanical rotational torque at the hub. These immense aerodynamic forces result in a mechanical dilemma. The rotor creates massive torque, but it turns at a sluggish 8 to 20 RPM. This is far too slow for a standard generator to produce utility electricity. Inside the nacelle, mechanical engineering takes over to solve this low RPM problem. The low-speed main shaft transfers raw torque from the spinning rotor directly into a transmission system. This internal architecture shows a planetary gearbox. It is designed to convert that low-speed, high-torque input into the high-speed, low-torque output required by the generator. With a gear ratio typically exceeding 100 to 1, the generator shaft is forced to spin at 1500 to 1800 RPM. However, the chaotic, fluctuating nature of wind causes brutal hammering stresses on the gear teeth. Because gearboxes are heavy, costly, and prone to fatigue, many fail within only a few years of operation. While mechanical gearing successfully achieves the necessary RPM, its physical fragility creates a bottleneck that limits the lifespan of the entire system. To counter gearbox failure, modern designs often eliminate the transmission entirely using a direct drive architecture. Here, the low-speed rotor shaft connects directly to a permanent magnet synchronous generator, which turns at the same 8 to 20 RPM as the blades. Generating power at such low speeds requires a physical trade-off. The generator diameter must be expanded to accommodate a much higher number of magnetic coals. This massive scale requires hundreds of kilograms of rare earth neodymium magnets per megawatt, which significantly increases upfront material costs. Whether an operator chooses the maintenance of a gearbox or the material costs of a direct drive ring, the mechanical energy has been captured. The generator now acts as the heartbeat for the grid. This ground-level photograph of a substation represents the rigid synchronization demands of the national power grid, which operates at a constant 50 or 60 Hz frequency. This creates an electrical conflict. To stay aerodynamically efficient, the turbine blades must constantly change their rotational speed to match wind gusts. Because the generator speed is variable, it produces alternating current with a constantly fluctuating frequency and voltage. Injecting this variable frequency AC directly into the network would cause catastrophic desynchronization and a collapse of the grid. The back-to-back converter serves as the critical electrical intermediary that resolves this synchronization problem. First, a rectifier takes chaotic AC from the generator and flattens it into direct current. This stores in a DC link capacitor, acting as an energy buffer. Finally, an inverter uses pulse width modulation to chop this DC into a perfectly synthesized grid-compliant AC wave. This power electronic sequence decouples the aerodynamic speed of the rotor from the electrical frequency of the grid, allowing both to operate at peak efficiency independently. These converters also allow turbines to inject reactive power and ride through grid faults, actively stabilizing the network. This chart follows the final path of the energy as it leaves the nacelle, drops down the tower, and passes through the substation to join the high-voltage transmission lines. The journey from wind to wire has maximized the physical limits of Betz's law, multiplied mechanical torque, and executed microsecond-precise power conversions. By combining aerospace fluid dynamics with heavy drivetrains and advanced power electronics, engineering has architected a stable heartbeat from the world's most chaotic, invisible force.